Finally, a word of warning or clarification at least. We just talked about sigma as being the width of a Gaussian, where that was the variance of the smoothing of the blurring. Last time we talked about sigma or sigma squared as the variance of a noise function, how much noise was being added. So in one case, when we're talking about the filter, the sigma is in space, okay? Whereas in the noise case, it's in intensity or it's in the value. The bigger the noise sigma was, the more noise you added. The bigger the blurring filter sigma, the more you're going to blur. So you have to be, and the reason they're both called sigma is they're both using a normal distribution, but one is over space and one is over intensity. We can show those two sigmas here. And by the way, here I'm using images that go from 0 to 1, partially because then I know how sigma varies with respect to the range of the image, and partially because the slides that I stole off the internet did this. All right. So in the top row, there's no smoothing going on. So we have a sigma of 0.2 in the noise. That's a lot of noise if the range is only going from 0 to 1 or let's say minus 0.5 to 0.5. A sigma of 0.1 is less noise. A sigma of 0.05 is less noise yet. But then we can smooth it, all right, with a Gaussian, right? This is the smoothing with the Gaussian kernel. And the more we smooth, the blurrier these things get. And so for the same amount of smoothing, the thing with the smaller amount of noise with the same amount of smoothing becomes even smoother, right? So this image here is even smoother than that image there, okay? But this is showing you those two sigmas, the two Gaussians. Almost always it'll be clear from context, but since I've had situations where students say, wait a minute, I thought the bigger sigma was, the more noise we got, and now you're telling me the more sigma is, the more blurring it is, the less noise we have. And I say, yep, two sigmas.